I just want to say first that my background is in computer graphics. And so regularly you find me working on research that looks a little bit more like this. But I've had so much fun being here. Everyone here has been super welcoming. And I was half expecting to get hacked at some point during the conference, but luckily I think I've made it through unscathed. But why am I up here? Well, in graphics, we use a lot of GPUs. We love GPUs. Love, 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 love. And they're not just for mining. We use them from everything from training robots in virtual environments, to ruining sandcastles, to running neural networks for model reduction, and so on. And so one day, I go to install extra hard disk for more storage so I can save all this wonderful work, and I hear some coil whine from the fans coming from my GPU. And it got me thinking about what other signals might be coming off the GPU. And even though I'm coming from graphics, I'd heard about these other great works, like how it's possible to use audio to uncover cryptographic keys, or more recently, how when it comes to neural networks, by probing an Arduino, you can uncover some of the weights from a handful of layers. And so I revisited these, along with many other inspiring works, and came to realize that previous methods have only ever looked at small networks or edge devices. So this likely probably wouldn't apply to GPUs, right? They're too fast, no? And so I did what any good PhD student does, and I bought the cheapest possible sensor I could on the internet. Literally, there was no world in which I could convince my advisors that I was doing anything useful. And so I just went for it, and here it is, a 47 kilohertz little FluxGate magnetic sensor that set me back a full $3. And I put it up to my computer, and you can see it there, along with a DAC converter that someone had lying around. And I ran some GPU code to get things cooking. I happened to be training a neural network classifier at the time, and so I wanted to check if there was anything coming out of my machine, or if it was all just a bunch of noise. And what did I find? Patterns, but not just any patterns, clearly identifiable patterns. And that should not have been very surprising. Why? Well, machine learning models running on a GPU are not just some magical random calculations happening in parallel. Neural networks describe a computational pipeline, a framework of building blocks and operations composed as layers, one after the other, where each new layer has to wait for the output of the layer before it has the values ready and it can continue. And the same logic applies for any subcomponents that make up network models, whether it's pooling operators, adding, multiplying, nonlinear activation functions, what have you. They all have this dependency on the neighboring layer's outcome, which means that even in the case of larger, fancier networks, and even in the case of parallel GPUs, a processor still has to synchronize and wait for the output of each layer, which sorts any complicated network into a topological ordering that we'll take advantage of later on. And by studying these EM traces littered with these synchronization points, it comes as little surprise to anyone in the side-channel community that each specific layer, in fact, produces an easily identifiable magnetic signature. So why does this matter? So you can see my network. So what? Well, networks are taking over everything. Everything. From vision applications to controlling robots, they're finding their ways into security and authentication frameworks as well. They're everywhere. There's numerous motives why someone might want to uncover a neural architecture. An attacker may want to just steal some intellectual property for profit, or they may want to circumvent some payment, wherein a company may invest some resources to develop a robust model and hope to recover those resources and by profiting when charging clients for its use. But by stealing the model, an attacker avoids paying for these services. Or perhaps they're looking to violate some sentries, and this comes up in the cases where a machine learning approach is taken to identify viruses or spam. An attacker increases their chances of deceiving or bypassing the model by uncovering its underlying neural network architecture. Another thing to keep in mind is that the graphics processing unit is the favored vehicle for executing a neural network. GPU chips are even being redesigned specifically with machine learning in mind. And as networks continue to grow and get deeper, and GPUs continue to get cheaper, and the popularity of running nets on these accelerated hardware, it makes sense to explore these two together, since any sort of vulnerability concerning these two is hot on the horizon. So in this case, we've arrived at a very capable threat model for a side-channel attack. Our proposed attacker has no prior knowledge of the target neural network. The model is taken to be developed, trained, and validated elsewhere. And since it's a side channel, snooping the network leaves no digital trace. The only accessible result will be a single inference. We don't even look at training, just the runtime use of the model. And so we'll assume that the model's code, memory, and design cannot be accessed without tampering the device or otherwise alerting the provider. And the attack is both non-invasive and passive. And in this case, we use a cheap sensor with no expertise required to operate, and it's very easy to acquire. And we treat the network as a black box while providing an input to it as someone might had they downloaded a network from some binary online. So what can we hope to gain from only the side channel information leaked from this targeted GPU in only a single scan? Well, the target is to extract everything we need to know about the network architecture in order to recreate it and train our own version, meaning that we'll need the layer and their order, the function types, along with the function widths, and anything that you need to define the individual layers' parameters. So that way we can recover any arbitrary network with any arbitrary layers and depth of layers. And our scope will target fully connected, convolutional, recurrent layers, along with activation, normalization, pooling layers, anything associated with ML architectures, because together these individual blocks span the components used by a variety of machine learning applications. And so now that we have the incentive to extract the model, an understanding of what it is that we're after, we present our approach. It contains 4 steps. First, offline, we generate a signal database by running lots of network designs and testing out models of various sizes and shapes. We also include some procedurally generated architectures where we stack together layers of random types, sizes, and parameters, and combinatorially throw them in ways that might not be common practice. This helps us sample the possible interplays of EM flavors that can occur between 2 adjacent layers in order to help us spice up our data set. Then, whenever we want to extract a network, we acquire a trace from the target GPU or its power cable, and then we run a window over the signal, which serves as input to a trained recurrent network, namely a BIOL-STM model that converts a single scan into categorical labels. This classification converts the signals into layers directly in place, and thanks to that computational unraveling that we talked about earlier, where the GPU has to compute the inference step by step, we also get the topological sequence as well of the network as a result. But at this point, we only have the types of layers and the order that they're in. Now we need to estimate the layer-specific parameter information that helps define each layer. And we do this by leveraging our data set yet again and looking for hints in the context of neighboring layers to the ones that we've identified. So by creating a feature of layer types along with voltage and timing information, along with adjacent neighbors, we can approximate the numerous parameters associated with this specific layer, whether it's the kernel size of a convolution, the output channel dimensions of an image, or how many neurons in a fully connected layer, etc. Now, because we can sample networks arbitrarily offline, the accuracy on these parameters is pretty good. But if we're off, we end up coming up with an invalid layer where the output to one and the input to another don't line up, meaning that these estimates cannot guarantee consistency between the layers. Even one wrong can lead to an invalid network design, which is why prior methods have decided either not to fully recover or to rely on an expert in the loop to fully recover the network layers, or sometimes assign them from a predetermined set of values. But getting this close and stopping just here is akin to playing a plumbing fall game where you start playing and then you call it a day after just a few clicks, which is why we additionally verify and clean up these proposed hyperparameter specifications by setting up an integer programming problem and performing a joint optimization. Using IBM CPLEX Solver, we do this, but in the interest of time, I'll defer to the paper for full details on how we can do this for all the different parameters. But it's worth noting that by estimating valid architectures for any shape and size layer, and by using this optimization, we make our approach more resilient to the network designs of tomorrow. And with that, the pipeline is complete, and we have a network model filled in that we can train and run. So let's see some results. We applied this method on a dataset generated from a single GPU's traces, starting with a GTX 1080. We also acquire a twin identical make of a model of a GTX 1080, and we use the signals gathered from one to extract models running on the other GPU. And we find that our attack is still successful, even on different new instances of the same hardware. We also test the GPU's transferability to quantify the importance of training on the right hardware. By collecting signals from a bunch of GPUs and combining them in training, in this case, we hold out the data from the target GPU, and we see how we would have fared. We find that, never having seen a specific card, we can still pose a threat by training on other cards similar to it. But as expected, having access to the traces from the target GPU throughout training produces even better results. We also look at our ability to perform transfer attacks, where we can look at how models perform when they attack themselves compared to the scores of attacking other models. And then we can see what happens when we try to extract models as a proxy. We find that our individual extracted models are akin to having the original model because of their fidelity. So in summary, GPUs can get faster and networks can get deeper, but that doesn't mean they're not vulnerable. A cheap $3 off-the-shelf 47 kilohertz sensor is all you need, and this works across GPU processors of all different makes and brands, and across also the popular network libraries and frameworks that people like to use for training. And in the end, we recovered networks with hundreds of layers accurately. So I just want to give a big thanks to my co-authors and my advisors, as well as all the funding sources and sponsors, and the libraries with which this wouldn't have been possible. And if you want to reach me, my contact information is all on my website. And with that, thank you guys for your attention, and I'll open it up to any questions. Thank you.